Okay, so the second lecture will be not on nucleosynthesis processes, but more on the technical part. How do you simulate nucleosynthesis? How do you set up what we call thermonuclear reaction networks? And time permitting, I want to talk about one of the ingredients we need, which are the nuclear physics ingredients, and what sort of the difficulties or uncertainties are there. So this is what we discussed in the first lecture. This is the same content, but with the view for the second lecture, which is focused on the nuclear physics, on the reactions. And so what this figure shows, again, proton numbers, number of neutrons, and it has all these colored arrows that indicate the different nucleosynthesis processes to give you an idea which nuclei are involved for these different processes. And you see with all the processes combined, we cover a large part of this nuclear chart, which means if we want to understand how these nuclei are made and where they're made, we also need to know through what processes or what nuclear reactions do we need to know. And so we need, the short answer up front is we need to know about all of these nuclear physics if we want to simulate the nucleosynthesis. So we need to know things. So with nuclear physics, I mean things like properties of nuclei, but also the reactions between nuclei and reactions between nuclei and leptons or nuclei and photons. And so I will come back to this point at the end of the talk with a specific example. All right. So what I'm going to do in the next couple slides is walk you through how we build the differential equations that are solved in a nuclear reaction network. Differential equations that you have to numerically solve if you're simulating nucleosynthesis. So let me start with two particles of type I and J, and their number densities Ni and Nj, and a cross-section between the two. And for simplicity, I'll keep my target fixed, so one particle type just sits there, and the other particle type is moving. So this is the projectile moving at some constant velocity. You can write the reactions per time and volume as the relative flux of particles times the number I, which are the projectiles, times the number of particles J, your target, times the cross-section between the two. Here are reactions, number densities, the velocity, number density of J, and the cross-section. Now this is too simple. We had a fixed target and a moving projectile. You can make it more general and say, well, they're both moving, so you need the relative velocity between the two. But the most general form is if both your projectile and your target particles don't have one single velocity, but follow velocity distributions. So then this expression for the reaction rates becomes this integral over the cross-section depending on the relative velocity, and then here you have your velocity distributions. Why am I doing this? Because in an astrophysical plasma, the nuclei are not monoenergetic. They typically follow Maxwell-Boltzmann distributions. So if you were to do this reaction in the lab, you build your target out of J and you shoot particle type I at it, and you measure, for example, a cross-section. In the star, both your particles I and J are moving, and they're moving with the velocity, the Maxwell-Boltzmann velocity distribution. So just as a quick reminder, then here's the Maxwell-Boltzmann distribution. So probability as function of energy. You have a steep rise that's roughly proportional to the energy, and then you have this long tail to high energies. And it turns out for astrophysics, this long tail is very relevant, so we'll come back to this. You have to do some manipulation, and I'm not going to go through the specific steps, but basically you're converting to center of mass coordinates, you carry out the integration, and you remember that the distributions are normalized. And then you can write your reaction rate R that we had before as number density of particles I times number density of particles J times this thing down here, which is the what we call the thermonuclear cross-section. So there's the cross-section here, there's the V for the velocity, and then these angle parentheses indicate that this is the integral over the distributions of velocity distributions of I and j. So your thermonuclear reaction cross-section down here is written out. So this is, if you take the two Maxwell-Boltzmann distributions and you do all these steps up here, you end up with an integral over the energy-dependent cross-section, an exponential term, the energy here, and then the constants are up front. So this now only depends on the temperature because you're integrating over all energies. It also means if we know sigma of E for all energies, we can get this thermonuclear reaction rate cross-section. The problem is in the lab, we measure this cross-section at a very specific energy or maybe at a few energies. So we have to do some extra work to be able to carry out this integral. In order to calculate this, but much more importantly, for what I just said, that we measure the cross-section only at one or a few energies, but we need the whole energy range, we're going to rewrite this part to make use of what we know about how the cross-section depends on the energy. And the simplest way to think about that is to think about charged particles. So for charged particles, the cross-section has different contributions, but two of them, we know what their energy dependence is. We know that the energy dependence for Coulomb barrier penetration is exponential to the minus energy to the power of 1/2. And the energy dependence of the cross-section due to the nuclear size is roughly proportional to 1 over the energy. And now we make our life very simple. We say, okay, we know the energy dependence of these two pieces, and then we lump everything else into what we call the astrophysical S factor. So you should think of the astrophysical S factor as being all the energy dependencies that are not either Coulomb barrier penetration or nuclear size. Why would we do this? Because for non-resonant reactions, so if you're not populating a specific level, all this rest that we lumped into the S factor is very slowly varying with energy. So basically, this S is almost constant or very slowly varying. So if you have to do an extrapolation from the energy for the cross-section, the energy that you measured it at, but you need other energies, it's much better to extrapolate something like S that's slowly varying in energy and then multiply that with the two terms where we know how it depends on the energy. There's many reasons why we can't measure the cross-section at all energies, and in particular why we can't measure it in many cases at the energy that's relevant for astrophysics. Because, for example, if you think about just a proton capture reaction, you need to penetrate the Coulomb barrier, but in the lab you have a specific energy of protons and a fixed target. So you have the situation we had in the first sketch. In the star, you have a velocity distribution, so you'll have protons at all of these energies. But in the lab, you can't, if you have a proton at this energy, in the lab your experiment won't work and you can't measure the cross-section. So you can measure cross-sections at some energies, and by dividing out these known strong energy dependencies, you're left with something that you can extrapolate more easily and more accurately, and then factor in those two components again, and then you have the energy-dependent cross-section for the entire energy range. So lumping everything into the S factor is really to make our lives easier for extrapolating to the energies we need. So if we take that, our cross-section is now the two known energy dependencies and the astrophysical S factor. And if we put this into the thermonuclear cross-section, this integral that we had before now becomes this. In this integral, the dominating term are these two exponentials here. And if you plot that, these two exponentials are this green e to the minus e over kt piece from here, from the Maxwell-Boltzmann distribution, and then the exponential e to the minus e to the negative 1/2 is there's a negative too many, is this piece here. And if you combine the two, your thermonuclear cross-section, so this sigma v here, becomes maximal in this blue area here. This is what we call the gamma peak. And the width of this peak is what we call the gamma window. So the rate is most effective at stellar energies in this energy range here. That's the which you find when you fold the two dominating exponentials in this integral here for the thermonuclear cross-section. So writing the cross-section in terms of S factor and the energy dependencies will also not only make extrapolating easier, but will also tell you what the at which energies the rates are most effective. So ideally, you want to do experiments here, but this is typically too low in energy. All right, so now we have the reaction rate as function of, so your thermonuclear cross-section, the two number densities, and I added in this extra piece which I didn't have before. This just takes care of if I and j are the same type of particles which you could have, then you have to take care of so that you're not double counting this, so there's this extra factor in front of that. So now we want to turn this into a differential equation or a time derivative, how the number densities of these species I and j change. Because for nucleosynthesis calculations in the end, what we want to know is how does the abundance of each nucleus or each isotope we're interested in, how does that change as a function of time? So now I turn this into the time derivative of, say, let's look at particle I first. So the time derivative of the number density of particle I, you can write as function of, so I'm looking at the reaction where I have I plus j going into O and M. So I and j change at the same rate, which is minus this rate, and so you're destroying, for each of these reactions you're destroying one I and one j, but you're making one O and one M. So the changes in number densities for I and j are proportional to minus this reaction rate, and the changes in number densities for O and M are proportional to plus this reaction rate. Now, what we really have to take into account is the number densities depend on the matter density. So really this time derivative has a component at fixed constant density, and it has a component as the density changes. But for nucleosynthesis, we're not interested in changes in the number density due to changes in density. What we're really interested in is just changing the number density or the number of species I and j due to nuclear reactions. So we want to do something to get rid of this piece here and only follow changes due to nuclear reactions. For this, I'll need to introduce abundances and mass fractions. So this is what I already said. You have the matter density rho, and your number density n depends on the matter density. So now we want to separate that dependence on the matter density out of our equations. So we define a quantity called abundance, typically denoted by capital Y, which is defined as the number density n divided by matter density and Avogadro's number. If you work out the units, your abundance has units of moles per gram. So now, if we follow, instead of following the number density, if we follow the abundance, we only follow changes due to nuclear reactions. On a side remark, but not important for the following discussion, is we can also define a mass fraction, and the mass fraction x of particle I, or species I, is defined as its mass number A times its abundance. And mass fractions are normal, so the sum of all the mass fractions of all the species in your gas are normalized to 1. So if you add up all your mass fractions, you get 1. Looking at this definition, if you add up all your abundances, this number will be less than 1. So with mass fractions, you can check that you're not losing any any mass. And if you have a code in each time step, you can check, do my mass fractions still sum up to 1? And that way you can check that you have mass conservation or nucleon conservation in your code. So from now on, we'll use the abundance that does not include changes due to density changes. So instead of having a time derivative for the number density, we now find the time derivative of the abundance. So using the definition of the abundance, this is what you get for the time derivative of the abundance. So now bringing back this reaction rate, the change in abundance is the rate divided by rho times Na. Or if you write it in terms of the thermonuclear cross-section, and instead of having number density of I and number density of J, now you have abundances of I and J. So now instead of having the Ni dt, sorry, I want to go back one more. Here. So using this rate, Ni times Nj times sigma v, now we're having sigma v, yi, yj, and then there's an extra factor of rho Na. And again, this fraction up front here takes care of if you're having a reaction where I and j are actually the same in distinguishable species. So far, we've derived this expression for nuclei or nucleons. Of course, you can also have other reactions like decays or reactions with photons and leptons. For decays, it's pretty straightforward. You can define a decay rate which takes the place of this reaction rate R here. So if you were to look, instead of a reaction between I and J, you're looking at the decay of I. You can write the time derivative of the abundance of yi as minus the decay rate lambda times the original abundance. For reactions with photons and leptons and also neutrinos, you can define an equivalent decay rate, that's why I put it in quotes here, where again, so if you have a reaction, say, photodissociation of a nucleus, so oxygen-16 being hit by a gamma, you can define a lambda, and so the change in oxygen-16 would then be the original abundance of oxygen-16 times this rate for the photodissociation rate. And so in terms of implementing this in a code, reactions with photons and leptons and also neutrinos look exactly the same as decays, beta decays do. So we have the two important pieces. We have reactions between two nuclei or nucleons, and we have the terms for decays, reactions with photons and leptons. Before we can write down the final equations we want to solve, we have to think about inverse reactions. So most of the reactions are the inverse of another reaction. So if you do carbon-12 plus alpha going to oxygen-16 and a gamma, then oxygen-16 plus gamma is going to carbon-12 and a helium is the reverse reaction. Of course, these two directions are linked to each other by time reversal invariance. So we can make use of that when we write the cross-section for the inverse reaction. So down here I have the thermonuclear cross-section for one direction, and over here is the thermonuclear cross-section for the inverse direction. And the two are related by e to the minus q over kt, where q is the Q value, so the energy difference between the products in the reaction and the reactants. So depending on what the Q value of your reaction is, that goes into how the two cross-sections are related. And then up front here, there's a piece that depends on the energy-weighted density of states, or in other terms, the partition functions. So that means for astrophysics, for nucleosynthesis calculations, if you measure the cross-section for one direction, if you know what your partition functions are and what your Q value is, you can find the thermonuclear cross-section for the inverse direction. Also, if you calculate the cross-section from a theoretical model, you only calculate one direction, and then you find the inverse, the thermonuclear cross-section for the inverse direction by multiplying with the partition functions and the Q value of the reaction. Even if when you implement it in a code, you calculate this cross-section or thermonuclear cross-section from the opposite direction. So you tabulate the cross-sections for one direction, you tabulate the Q values for all your reactions and the partition functions, and then you calculate on the fly the opposite direction. So with all of that, we can write down our differential equations that are the fundamental equations in a nuclear reaction network. So for each nuclear species we're trying to follow, we have one equation that looks like this. So the change in the abundance of that species depends on all the reactions that either make or destroy I. Typically, we group them by types of reactions. So you see here are the ones like decays, reactions with photons, leptons, and neutrinos. And then over here are the reactions between nuclei or nuclei and nucleons. But really, what this means is just you sum the contributions from all the reactions that either make or destroy I. Yes?
When you're doing these kinds of calculations, is you vary lambda with time, or you just sort of assume that you're in an environment where your photons and leptons and neutrinos are sort of in a steady state distribution?
So that's a very good question. So here, obviously, I talked about the energy dependence before. Here, I completely ignored it. So it depends on the type of reaction. So typically for beta decays, we assume they're constant. So we just use one decay rate, temperature independent. But for reactions with photons or with leptons or with neutrinos, this lambda is actually time dependent. So when you define that, or when you calculate that, it depends on the environment, on the astrophysical environment. So this can be either a constant lambda or a time-dependent lambda, depending on the specific reaction. All right, so with that question, let me point out that first, that this is where implicitly the conditions in your astrophysical scenario go into this equation. So say if you want to calculate nucleosynthesis in a core collapse supernova, your temperature and density evolve as a function of time. So that will go into this differential equation. The density here explicitly, the temperature implicitly in this thermonuclear cross-section, and also into this lambda. The other pieces are these capital N's and the capital N and this fraction here. That specifies the number of particles that are created or destroyed in a reaction, and you also take into account if you have reactions between identical particles. So if you have, for example, a triple alpha reaction where you have 3 helium nuclei reacting with each other, you destroy 3 helium particles to make 1 carbon-12, and you don't want to count that reaction 3 times because there are 3 alphas involved, so you have these factors here in front that take care of these counting issues. Yes.
For a triple reaction like that, the second term has to be modified?
Yes, we actually need a third term here that is on the next slide. I'll come to that in a second. Very good question. So here you have the abundances, and then here's the decay constant, or a decay constant in quotes if it's temperature dependent for lepton or photon reactions. So I meant to use this equation. I just put the wrong one in the previous slide. So you're absolutely right. For reactions with three-body reactions like the triple alpha, these are not described by these first 2 terms. So for these, the thermonuclear cross-section here is for the 3 particles. Of course, you need to know how many, if there were 3 different types of particles, what the abundances of all 3 are, and then you again have to take into account this extra counting factor. And because you have 3 abundances here, the density goes in squared, and the Avogadro's number goes in squared. So this first piece, again, are decays, photodisintegrations, and lepton reactions. This green piece here is standard 2-particle reactions that we use to derive most of this. And then if you have 3-particle reactions, you would have a term like this. So now you have a differential equation for each species I that you want to follow. If you do Big Bang, this is a dozen species or so. If you do hydrostatic evolution, this might be 100 species or so. If you do explosive nucleosynthesis for core collapse, you want to include maybe 1,000 or so. If you want to do new P process, it's more like 2,000 because you need to go beyond the iron group. If you want to do R process, this goes up to maybe 5,000 or 6,000. So that's where the computational challenge comes in. Because all of these, imagine you have, let's make it simple, we'll just follow 100 species. So you have 100 of these reactions, but they're all coupled because as you say make I, you need to destroy other things. So the abundance of I depends on the abundance of all other species that you're following. So they're first order, but they're coupled. And the number can be quite large depending on what scenario you're simulating. So the next thing I want to talk about is how to discretize it and put it into a code. So the way we discretize this differential equation, the most straightforward way is to say the abundance at the new time minus the abundance at the old time divided by the time step depends on either the derivative at the old time or the derivative at the new time. And then there's these theta factors and 1 minus theta in front to show you that there's 2 different ways of doing this. So if you do an explicit method, your discretization, so theta would be 1, which makes this term go away. So this just depends on the time derivative at the old time. In an implicit method, fully implicit method, your theta would be 0. So this term goes away, and your discretized, the abundance of new time minus abundance at old time divided by the time step will depend only on the derivative of at the new time, which makes solving more tricky if you need to know what y, the derivative of y at the new time is. This method, or both these methods, are accurate to first order in time, and the accuracy improves inversely with time steps. So if you make the time step smaller, the accuracy goes up. It turns out for nucleosynthesis in astrophysics, the forward Euler method, so where you set theta to 1, so you only need to know the derivative at the old time, performs really poorly because the time scale for the different reactions can be very, very different. So because of this large range of time scales, we call this a stiff system of differential equations, and the method that works much better is an implicit method where you need to know the derivative at the new time. So solving this differential equations with a backward Euler method or implicit method is equivalent to finding the zeros of this equation. So you move this piece to the other side. So this is the equation we had before. So we try to find the zeros of this equation. And typically this is done by a Newton-Raphson method where you find a trial abundance given by this expression, and you do it iteratively until you find the zeros of this equation, which lets you solve this and get the new abundances at the new time step. So that when you do this, you need to build a Jacobian matrix here, and you have to solve it. And this is where the computational costs of nucleosynthesis calculations lie. For each time step, even if you only, in an ideal world, you only needed 1 iteration, you still have to build for each time step. So each time step you have 1 iteration to find the zeros of this equation. So you have to build your Jacobian matrix, and you have to solve it. Of course, if you do an R process calculation, this becomes quite big if you follow 5,000 or 6,000 nuclei. But the same way the problem forced us to use an implicit method, the problem has another property that makes our life easier again. And this is what we define as the sparseness of the matrix. So in general, if you take a mix of species, every species can react with every other species, which would make this Jacobian matrix dense, because each combination of two species can react with each other, so there's a reaction rate there. But in reality, you have the Coulomb term that suppresses, for example, captures of heavy nuclei and other heavy nuclei, with a few exceptions. Also, photodisintegration reactions predominantly emit nucleons, so neutrons or protons, and alpha particles. So we only need to consider about a dozen reactions. For each species, we only need to consider about a dozen reactions that link this one species with its, what I call, nuclear neighbors in a second. So capturing, so that's the original species plus a neutron plus a proton or plus an alpha, and whatever you get to if you have a decay. Yes?
How does the computational cost of the backward Euler method compare with, say, RK2 or RK4?
So I'm not 100% sure, because I've only used backwards Euler method, which works very well. I've not investigated if you use different methods. It's cheaper. Okay. So by making use of what we know about the system, our matrix, so this is a representation of the matrix where each column and each row has are the species you're following. So in this example, you'd be following 300 species, and wherever you have non-white space in here is where you have a reaction that can take place and where you have a non-zero matrix element. Typically, you put your neutrons and protons and alphas at the beginning, so you have non-zero elements up here, and then along a white diagonal, but most of the rest of the matrix is empty. So when you solve this Jacobian matrix, you can make use of sparse matrix solvers, which makes it computationally a lot less expensive. Yes?
I can't help but notice it's asymmetric. So those dots in the columns don't match up with the dots on the rows on the side of the diagonal.
You mean these dots here?
Yeah, okay. So what's happening there?
I think they should be symmetric. I think that's a resolution issue. Yeah, I have more dots on my screen.
Okay.
No. So these are basically things like carbon 12 plus carbon 12. So yes, there's more dots here. All right, so by what we know about the system, we have to go to an implicit method, but we can use sparse matrix solvers. And computationally, it makes a difference using a sparse matrix solver. And the other thing that's cuts down on your computational costs is if you, instead of storing this matrix, every element of it, if you store it because it's sparse, there's specific formats to store sparse matrices where you only store the location and the value of the non-zero elements. So you can also cut down on memory use if you know that you have a sparse matrix and you use these specific formats for sparse matrices. All right, so we have our differential equations. We know how to solve them. So the hands-on activity would have been yesterday to do a nucleosynthesis calculation, but that's got cut by American Airlines, leaving me stuck in Raleigh. All right, so we know that the differential equations we're solving. Let me spend a little bit of time explaining how we model nucleosynthesis. So in principle, in an ideal world, you would want to do, say, your core collapse supernova explosion and your nucleosynthesis in 3 dimensions with all the physics you know, everything at once. So you want 3-dimensional hydro, you want the reaction networks. Let's assume core collapse supernova you make an R process. You'd have to follow 5 or 6,000 nuclei, you have to do 3D hydro, the neutrinos and everything. So this becomes very expensive. So typically what we do is, first of all, sometimes we reduce the hydro to go to 2D or 1D. That's not what I want to talk about. So what we But what I want to talk about is typically, one of the compromises is to put a reduced network into the hydro simulation. So you only pick reactions that generate energy, because those are important for the dynamics. But then reactions that just change one nuclear species to the other but don't liberate a lot of energy, they won't change your hydro simulation, so we exclude those. And then in a second step, we use the temperature density evolution from the hydro simulations and recalculate the full nucleosynthesis with a network where we follow all the species we're interested in. So from an ideal world of fully coupled between hydro and abundances, a lot of times, and a lot of the research I do, is a post-processing approach where you do the hydro simulations with just the reactions that are relevant for energy generation. Then you take that data and you feed that data into a nuclear reaction network. Or now you don't have to minimize the number of species you're following. Now if I do a new p-process calculation, I can follow every species that I think could possibly be relevant and do it in a post-processing approach, decoupled from, in a separate step from the hydrodynamics. All right. So we have the differential equations. We have how do we get the other piece, mainly the hydro. So the hydro, the density temperature evolution, I mentioned that before. Here's your density, go into the thermonuclear cross-section. They go into these decay rates in quotes for photodisintegration reactions and reactions with leptons and neutrinos. But the other piece we need, if we want to solve these equations, is the nuclear part. So we need half-lives for beta decays. We need cross-sections that go into here. So we need to know the nuclear physics. And ideally, we want to measure all of these quantities. So we can measure specifically for stable nuclei or long-lived nuclei. We can measure their mass. We can measure half-lives. We can measure some spins and levels. So we can measure some cross-sections. So for example, we can measure cross-sections, any reaction that has protons plus a nucleus. We can build, if it's a stable nucleus, we can build a target out of that nucleus and shoot protons at it, or we can use a hydrogen gas as a target and shoot, even if it's as long as it's long-lived, we can shoot a radioactive isotope at it and measure the cross-section for that isotope plus protons. For example, neutron reactions, if you have a stable or long-lived target, that plus a neutron works. But if you want to do something, for example, a neutron interacting with a short-lived radioactive species, well, you can't measure that. So we need to rely on theoretical predictions. And if you remember your chart of isotopes that I showed in the very beginning, most of the nuclei involved, say in our process calculation, we have zero experimental measurements because they're very, very short-lived. They're very, very far from stability. It's very, very hard to perform an experiment. So we rely a lot on theoretical predictions. So the last chunk of this lecture I want to use on the specific example of the neutrino P process, showing you what we know about nuclear physics and what the uncertainties are and how they impact our nucleosynthesis predictions. So for the neutrino P process, remember it's on the proton-rich side of stability. So it involves unstable nuclei. They're short-lived. Some of them are more short-lived. And it involves proton captures, and it involves NP reactions, so neutron capture reactions. So it turns out most of the reaction rates you need for new P process calculations are actually from theory predictions. Typically, the model is used for these theory predictions are statistical model or Hauser-Feshbach calculations, because if you have thousands of nuclei, you have 10,000 of reactions, and you need a model that sort of globally works, even though you could do better for specific reactions with a different model. Into these theoretical reaction rate predictions, you need to know what goes into there are nuclear masses, spins, information about levels. So anything, even if you can't measure the cross-section, if you can measure one of these pieces that go into the theory predictions, that's better. One thing that's with current technology is has become more accessible to measure even for short-lived isotopes are the nuclear masses. So you can do measurements with penning traps, which has been done at different places. This is in Germany, ship traps in Germany, UFO traps in Finland, CPTs at Argonne. So you can measure the mass of these unstable isotopes, which will then improve your theory predictions for the reaction rates that go then into the nucleosynthesis calculations. And probably all of you are aware that we're building the EFRIP facility with one of the goals being that we can access even more nuclei that we could not access experimentally before to get more information that can go into these theory predictions for the reaction rates. So here's, again, part of the chart of isotopes relevant for the neutrino P process. So here's your strontium, yttrium, zirconium region, goes up to close proton shell at 50 at 10. And the color coding, so black are the stable isotopes. All the blue ones are on the neutron-rich side of stability, so you can ignore those. And then the other half of this chart here is color-coded if we have measured, so this is back from 2008, so there's a few more boxes that should be in a shade of red. But basically if it's green, and I just realized this is probably hard to distinguish, so there's green out here and some green in here. These are all isotopes where we have not measured the mass. The red ones, or a shade of either this light yellow, dark red, or middle red, are the ones that have been measured recently with one of these 3 experiments. So we have a penning trap measurement for these masses around here. Most of them are very, yes?
Why don't you have close to the line stability, you have unmeasured closer to the line?
These here?
Yeah.
So some of them have now been measured. So you have to produce them if you want to measure them.
Right.
So in the penning trap, you need an individual nuclei of this species. And so some of it is limited by what you can produce. So for example, if you want to measure, I don't know, niobium-92, you have to somehow produce niobium-92 and extract it from all the debris you make, so you can then put it in the penning trap. So it's not just the half-life, but also producing the isotope that limits your ability to measure it. So most of these masses that have been measured here were very close to the theoretical predictions from the atomic mass evaluation, but some of them were quite different. And so what we did here is we did new P process nucleosynthesis calculations, once using rates based on the theoretical masses and once using rates based on these newly measured masses here. And so this is what is shown in the top left corner here. So I show abundances relative to solar as function of the mass number, and there's open down-facing triangles and filled upwards-facing triangles. The open triangles are using theoretical masses, so AME stands for atomic mass evaluation. The filled triangles are the rates based on these experimental masses that have been measured here. And you can see that for most of these nuclei, it doesn't make a difference, except for right in here, strontium, yttrium, zirconium. There is some change, some local change of the final abundances. And this is because of the technetium-88 mass that has been measured, and that is quite different from what the theoretical predictions was. So the ratio between doing a proton capture on the molybdenum-87 to technetium and a neutron capture on this molybdenum going to niobium has changed, and also the proton capture on technetium-88 going to ruthenium-89 has changed because of this mass having changed. So then you redistribute the path here a little bit, which when you decay back to stability will redistribute your final abundances in this strontium, yttrium, zirconium region. So this is an example of where measuring masses can confirm the theoretical predictions, and in cases where it doesn't confirm, we know what the uncertainty in our previously predicted abundances is due to having a mass that wasn't quite what it turned out to be experimentally. So masses are one piece that goes into the reaction rates. The other thing is the reaction rate itself. So remember, we need the cross-section at every energy because we integrate over all the energies. So even if we had a measurement at a few energies, we still have the whole range where you have to extrapolate. So the energy dependence could be or is uncertain. So another thing we looked at is what if not worrying about where the uncertainty comes from, but what if the thermonuclear cross-section, or the thermonuclear cross-section, hence the reaction rate, has some global uncertainty. So maybe it's off by a factor 2, which is well below what people who do these reaction rate Hausser-Feshbach models say it could be. And so here we took a factor 5 and just multiplied or divided individual rates by this factor to see if this rate is uncertain, do the final abundances change? And of course, I'm showing you the ones here where it actually makes a difference, and not all the ones we looked at where it doesn't make that much of a difference. Again, this is for a new P-process calculation, so everything's the same. It's the same hydrodynamic conditions. Everything's the same except for example, changing the reaction rate for germanium-64 Np, or changing the reaction rate for nickel-56 Np, changing the reaction rate of blank, that's 96 palladium Np. And you can see that for palladium, I'm going to start with the top right corner. So changing the reaction rate for Np reactions in palladium, if you look at the final abundances shown here, the 3 lines, solid, dashed, and dotted, are pretty much on top of each other. So you might have some local differences, but overall your pattern looks very much the same. This is not the case for nickel-56 Np and for germanium-64 Np. So these two plots show the same information but displayed slightly differently. So I'm showing abundances relative to standard. So I divide these 3 lines by the black line. So solid line divided by solid gives you a straight line at 1. So that's the reference case. And then the other 2 lines, they're also divided by the standard, the abundances from the calculation with the standard rates. So here, this peak here, you get more if the rate of germanium-64 Np is smaller. And then again, your tail, out here, you get higher abundances versus in the middle. So this region here, you get lower abundances if this rate of germanium-64 Np is lower. So germanium-64 Np is, you remember germanium was that nucleus with the very long beta decay half-life, so we looked at this first. There's some change, but not as significant. The one that really makes a difference for the neutrino P process is nickel-56 Np. So here you can say if you change the rates by factor 5 up or down, you pretty much change the abundances in the whole range. So these plots start at a mass number 56, so right at the nickel. Pretty much everything heavier than nickel you'll change, and it's affected by changes in this rate. The reason is you need neutrons on germanium-64 for the new P process to start. If you use a lot of neutrons on nickel-56, those are going to not be there anymore once you have made germanium-64 and you need these neutrons for the new P process to continue. If you make the rate bigger, this red dotted line, your abundance distribution ends much earlier. So so for the neutrino P process, it's not just the reactions along the path, like the 2 examples on top, but it's also reactions on the iron group that strongly affect your final abundances. And so this work in looking into the effects of nickel-56 Np has now triggered several experimental groups to think about if there's a way to experimentally measure anything that can constrain this rate better than it is now. You would think with the importance of nickel-56 that this has been measured, but nickel-56 is unstable and it reacts with neutrons. So you can't do a direct measurement of nickel 56 NP, or even just nickel 56 plus neutron reactions. So there's several ideas of going the opposite direction to at least measuring, maybe getting levels in nickel 56. So there's 3 different groups that, because of this result, have started thinking about what they could do to measure something that improves the prediction for this rate. Yes?
I just want to make sure I understand. You're scaling the sigma b bar by factors of 5?
Yes. So with the rationale that at high energies, we're scaling the sigma v and the inverse direction to keep the equilibrium the same. So at high temperature, and it's basically just moving the whole thing up or down. At high temperatures, where you're in equilibrium, it shouldn't change the abundances if both directions are higher or lower, and then you're effectively probing what the low energy contribution of a different rate will have on the final abundances. I'm going to only briefly talk about this, given that it's already 12:25. So all of these investigations here were made with a particular model for the neutrino P process, a particular hydro model. And of course, you can argue, well, is it worth to base an experiment on this, having used just one particular model? So we also looked at, is there anything we can say that is trajectory independent, or meaning independent of which mass parcel you're following in the simulation and what is specific your simulation is. And it turns out, at least for the neutrino P process, that because of the physics that in the neutrino P process, so first of all, you have an equilibrium between P gamma and gamma P reactions for most of the neutrino P process. So by looking at, just assuming this equilibrium and looking at which isotope for each element is the most abundant one, you already can make a prediction on which nuclei, reactions with which nuclei will be the most important. So this is what we did here. We calculated equilibrium abundances, and from that, so we calculated equilibrium abundances for P gamma gamma P equilibrium, and we looked at which is the reaction, the largest reaction that destroys each of these isotopes. So that's what the arrows indicate. And from this, we could predict which ones might be the most important ones. And since we've done, for different trajectories, brute force varying all of these rates individually, and it turns out it's really the ones that you can find from these considerations are the ones that are the most important. So it doesn't depend. You can use a specific trajectory to show how big the abundance changes are, but the predictions, which ones are important, are independent of your particular trajectory you're using, of course, assuming a neutrino P process condition. So all of what I've said here is specifically for the neutrino P process. So this is a nice conclusion we found here, because that means we can predict, it doesn't really matter which trajectory we use to predict and tell which nuclei and which reactions are important, and to give experimental groups an idea which ones might be interesting to look at. So this, I took this from another talk that I've given on this topic. So this resulted in a long list of reactions and that are important with characterizing which energy ranges they're important and what their priority is given by how much they affect the final abundances. All right. So with that, I told you how to build nuclear reaction networks, what we need to solve them, so hydrodynamics and the nuclear physics, and how, especially the nuclear physics part, because I'm sure you've heard a lot about the hydrodynamic simulations last week, how the nuclear physics knowledge is important for accurate abundance predictions. Thank you. Yes. No, there's not yet. There's other groups that have done that, looking at. So there has been a study by Gail McLaughlin at NC State and her graduate student on looking into the sensitivity of neutron capture reactions I'm involved in an ongoing project to look at sensitivities of beta decays. There's been sensitivity studies for the gamma process that I talked about in the morning. So there's been sensitivity studies for S process. So typically people that do nucleosynthesis predictions for a particular process also, as a natural thing to look at, do the sensitivity studies. Yes?
It's surprising to me that the reaction rates for 56 are so poorly constrained. Do you have any insight as to why that is?
So particularly for nickel 56 and P, it's just because both reactants are unstable. So you can't make a measurement for nickel 56 and P, because nickel 56 is unstable and your neutrons are unstable, and you can't have a neutron target, you can't accelerate neutrons. So it's very difficult to set up an experiment for this.
Yeah, so I understand that nickel 56 is unstable, but it's got a relatively long half-life, certainly long on the time scale of experiments. Or is it just a production problem?
It's a production problem. It's also, if you have a nickel target, you have nickel 57, nickel 58 in there as well. So it's also, how do you separate out the 56 component? And if you were to build a target, so we looked into this a little bit, there's some of the gamma rays that come out of these unstable nuclei are in the energy range that is extremely hard to shield.
Yeah.
So
So I think I understand a little bit of what you're saying, though, is normally if you're using some radioactive isotope, you're accelerating that thing onto some target.
yeah, so
But you can't make a block of nickel 56.
Yeah.
And you can't make a block of neutrons. Is that kind of what you're getting at?
yes, and so the ways to measure this would be you make a block of neutrons and shoot nickel 56 at it, which you need to make nickel 56 pure. You make a block of nickel 56 and shoot neutrons at it, but you can't accelerate the neutrons because they're not charged. So it's here for this particular reaction, there's a combination of difficulties that come into play.